Hey gang, I just want to talk about one specific probability problem that you may have heard of before. It's called Monty Hall problem. The Monty Hall problem basically said that there were 3 doors, and behind one of the doors was a car, and behind the other 2 were goats, and you wanted the car. And after you picked a door, the host would reveal a goat behind one of the other 2 doors. And then he would give you the option to stay with the door that you picked or to switch to a different door. And a lot of people get confused about what the probability, whether it's better to stay or to switch. A lot of people think that, well, once the host eliminates a door, let's say you pick door 1 and he eliminates door 3, that it's a 50-50 chance now. And so it doesn't matter whether you stay or switch. But let's think about this. The probability that you pick the correct door right off the bat is 1 out of 3. So if you stay, there is a 1 in 3 chance that you will win, because there's a 1 in 3 chance that you pick the right door. Okay? Doesn't matter what he eliminates, the probability that you pick the right door was 1 out of 3, so if you stay with it, it's still 1 out of 3. If you switch, okay, switching is a little bit trickier to think about, but think about it this way. There's a 1/3 chance that you pick the right door right off the bat. So if you switch, now there's a 0 probability that you're going to win. So 1/3 of the time, you've picked the right door, you switch, and so now you've lost. But 2/3 of the time, you switch, and now there's a 100% chance that you're winning. So 2/3 of the time, you originally picked the wrong door. So if you switch, now there's a 100% chance that you're winning. So 1/3 times 0 is 0, plus 2/3 times 1 is 2/3. So switching gives you a 2/3 probability of winning. Let's think about this another way. Okay, you could have car, goat, goat. You could have goat, car, goat. Or you could have goat, goat, car. So let's say you pick door number 1. Well, in the first scenario, if you stay, you win. In the second scenario, if you stay, you lose. And in the third scenario, if you stay, you lose. So 1 out of the 3 times when you stay, you win. Let's look at switching. Okay. In the first scenario, okay, the host is going to eliminate one of the doors. If you switch now, you're going to lose. Okay. Second scenario, the host eliminates one of the doors. This time, if you switch to door number 2, you're going to win. So you've got 1 loss, 1 win. And then in the third scenario, the host eliminates one of the doors. And now let's say you switch from door 1 to door 3. You win again. So in the first scenario, you switched and you lost. Second scenario, you switched and you won. Third scenario, you switched and you won. So you won 2 out of the 3 times. So in this problem, staying with the one that you picked, you only win 1/3 of the time. Switching, you win 2/3 of the time. It's often easier to think about this with 1,000,000 doors. Okay. 1,000,000 doors. The probability that you pick the right door is 1 in 1,000,000. So if you stay, if the host opens up all of the other doors except for 1, and you stay, there's a 1 in 1,000,000 chance that you're going to win, because there's a 1 in 1,000,000 chance you pick the right door. But if you switch, okay, then there's a 999,999 in 1,000,000 chance that you will win. Okay. Now things get a little bit more confusing when the host might open different amounts of doors. So for example, let's say we had 4 doors. Okay, door 1, 2, 3, and 4. And let's just look at a couple of examples here. Let's say that we could have car, goat, goat, goat. We could have goat, car, goat, goat. We could have goat, goat, car, goat, or goat, 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 car. Okay. So again, let's assume that you pick door number 1. If you stay, you're going to win 1/4 of the time. Now, I'm assuming again that he eliminates all but one door. So you pick door number 1, he eliminates 2 other doors. Okay. So if that's the case, if you stay, you win 1 out of the 4 times. If you switch, you win 1, 2, 3 out of the 4 times. Okay. But what happens if the host doesn't eliminate 2 other doors? He only eliminates 1 other door. Okay, so let's set that up. Okay, so goat, goat, car, goat, and goat, 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 car. So now, again, you're picking door number 1. This time, though, the host only eliminates 1 other door. Okay. So now, if we look at this, if you stay, your probability of winning is still just 1/4. So that didn't change. But now your probability, if you switch, well, in the first one, that's 0. Okay. In the second one, if you switch, you have a 50-50 chance. Okay. So that's 1/2 probability there. Here, in the third one, you have a 50-50 chance. And in the fourth one, you have a 50-50 chance. Okay. So in this case, we have basically 8 possibilities here. Okay. You switch to door 2, you switch to door 3. In scenario 2, you switch to door 2, you switch to door 3, and so on. So out of the 8 possibilities, 3 of them are winners. So switching gives you a 3/8 probability of winning. Okay. So by only eliminating 1 door, he left you with 2 doors to pick from, and that took the probability of winning from 3/4 down to 3/8. Okay. So basically, let's look at this a little bit differently. We could say that our probability with 4 doors, opening 1, okay, the probability of winning if we stay is just 1 out of 4. But the probability of winning if we switch, well, there's a 3/4 chance that we picked the wrong door to begin with. Okay? And then he's going to eliminate 1 of the doors, so that takes us down to 3, but we can't switch to the door that we're currently on, so we only have 2 doors to choose from. 1 of those doors is a winner. So the probability that we pick the wrong door and we switch to a winner is 3/8. Okay. So let's think about this in more general terms. Here, and now this is assuming that there's only 1 prize, okay, the probability of switching and winning, well here, let's do staying first. The probability of winning if we stay is just 1 divided by n, where n is the number of doors. Okay. Here, we have the basically the complement to this. So if there's one way to win, that means there were 3 ways to lose. So that's just n minus 1 over n. Okay? So there are n minus 1 ways to lose. And we still have n doors. Now, if we're going to switch, so this means we picked a loser, so there's still one winner out there. So if we switch, there's one chance at winning out of, well, we're starting with n doors. We're subtracting one door that we picked, and we're also subtracting so many doors that the host is going to open up. So we'll call that H. Okay? So in this case before, we said the host opened up one door as well. So the door we picked plus and the one door that the host picked means we subtracted 2 from the 4 doors, and we were left with 2. So this we could multiply across. We get n minus 1 over n times n minus 1 minus h. Okay? So now we could do this for any number of doors. Okay? So for example, let's say we had 7 doors, and the host was going to open up 3 of them. Okay? Well, our probability, if we stay, is 1 over n, 1 over 7. Our probability if we switch is n minus 1, so 6 over n, 7, times n minus 1 minus h. So 7 minus 1 minus 3. So that's 6 over 7 times 7 minus 1 is 6, minus 3 is 3. Gives us 6 over 21. And we could reduce that to 2 over 7. So in this case, the probability of switching and winning would be 2/7. Okay? And again, that's because we have the probability that we picked the wrong door to begin with times one winner divided by the number of doors that are still left available to us. Okay? And that's what this n minus 1 minus h is this is the doors available to switch to. Okay? So this is kind of a complicated problem. I would hope that you could understand the basic Monty Hall problem here, where you just had the 3 doors. Okay? But this is a more complicated problem that might be a question I ask you as a challenge coming up. So just a variant of the Monty Hall problem.